I am responsible for monitoring the glaciers in all of Washington's national parks. And so what I want to do today is give you an update on their status because, as you'll see soon enough, they're changing pretty fast. So I will be here after the lecture to answer questions if you want to stay. And I don't mind if something is really not clear. If you interrupt me during the talk and ask me to explain it further, that's fine by me. So with that, I'm going to jump right in. And I'm going to start out with a really basic definition of what a glacier is. Okay, so we all know glaciers are made of ice, but they also include snow and rock. And one of the ways that we can tell the difference between a glacier, we can see here in a snowfield, are these cracks in the surface called crevasses. Okay, so what happens if anybody, you must have all dropped a piece of ice, what happens when it hits the ground? It shatters, it cracks, because ice is brittle, right? So these crevasses are evidence that this glacier is moving off of that mountainside. And we have a lot of glaciers in this part of the world because our climate is wet enough and higher in the mountains, it's cold enough that the snow that falls in the winter doesn't melt the following summer, so that it's sitting there and it gets snowed on again the next winter. And after several years of snow on snow, eventually you'll form a glacier. So these glaciers, they build mass higher in the mountains and transfer it from what we call the accumulation zone down to the bottom or the terminus of the glacier where melting is fastest, right? So the farther up in the mountains you go, it gets colder. The lower you go, the warmer it gets, about 3.5 degrees for every 1,000 feet. So these glaciers, as you'd expect, are extremely sensitive to the weather, and particularly temperature. And the obvious direct relation is that the warmer it is, the faster the ice melts in the summer. But the glaciers we have are also getting affected by warmer temperatures in the spring and the fall. And the way that's working is they're getting rained on at times when they used to get snowed on. Right? So we say the accumulation season, the winter is shrinking as the summer melt season grows. And so the glaciers, I say, they're getting kind of a double whammy. They're melting faster in the summer and they're getting less snow in the winter. And as you'll see in a few slides, the changes are pretty dramatic in these glaciers. So these glaciers, we can tell at the end of the summer, usually late September, when we figure the melt season's ending and the accumulation of snow is going to start, to identify these two zones on the glacier, the zone of net gain and the zone of net loss, and the difference between these we call the equilibrium line altitude. Okay, and I love this image because I think it really illustrates well, because you can see I hope you can see these different shades of gray that represent different equilibrium line altitudes. In this case, the image was taken in 2005, and it was after 3 consecutive years of increasing summer temperatures and less snowfall. So we see the ELA rising. But the glaciers are very sensitive to temperature, as I said, and typically at the end of the year is a good time to see how the glacier did in that 1 year. And for the glacier to have been in balance for that 1 year, that equilibrium line should be low enough so that 2/3 of the glacier is still covered in snow at the end of the summer melt season. So we have some pretty substantial glacial resources in Washington's national parks. Here are the numbers of glaciers, and these are glaciers bigger than 0.1 square kilometer. Most of them are in North Cascades National Park, but we've got quite a few in the Olympics and some really big active glaciers on Mount Rainier. So for the Park Service, there's a lot of reasons why we're interested in these glaciers, and I want to just touch on these for a minute. Aesthetically, I don't know how many of you have been to a glacier and seen the color of the ice? It's pretty unforgettable, isn't it? This is an ice cave that I took a picture of in the late 1980s. This ice cave is gone, but I was really haunted by the color of that ice. And you know, there are other subtle effects on the aesthetics of the mountains. Our lakes that are fed by glaciers get these beautiful shades of blue and green in the summer because of the melting of the glacier. And the glaciers, as they slide off the mountains, are grinding the rock beneath them and producing what we call rock flour. And that rock flour gets into our lakes and streams and gives them these fabulous colors. And so this is Silver Lake, which is an incredibly deep cirque lake. And you can see the change that occurs from the spring when there's no glacier melting yet, and the lake's dark blue to the summer when it's full of glacial flour. Now we also are aware that our glaciers are habitat for some species. And that shouldn't surprise us because I don't think there's any square inch of this planet that isn't habitat for something. It doesn't matter if it's a hot vent at the bottom of the ocean or a glacier. And so we have species like the ice worm that inhabit the glaciers, and they live on pollen and other things on the glacier. We don't know a lot about them, but on many occasions I've seen birds like the rosy finch come and eat the ice worms. And the ice worms, as you would imagine, are really sensitive to the ultraviolet radiation. So they go down into the glacier when the sun's high in the sky in the day, and then they come up late in the afternoon or when the cloud cover comes, and then the birds come. And so not only are the glaciers habitat, but they're part of our alpine food web. And again, this is something we don't know very much about, but just another reason why we're interested in these glaciers. Now we get about 40,000 backcountry visitors to the North Cascades Park every year, and a lot of them are come to mountaineer. And they come to the North Cascades because they can get what I call the complete mountaineering experience, right? They can do ice travel, glacier travel, ice climbing in addition to the rock climbing. And so a lot of our main climbing areas, in fact, most of them, the routes cross on glaciers. So as these glaciers change, the access points into the park change for the climbers. But probably one of the two most important reasons why we're interested in these glaciers is that they're really important sources of fresh water. And if you think about it, when the glaciers are melting the most is in the summer when we get very little rainfall. And it's a beautiful thing in this part of the world. You get water in your rivers and lakes without rain. And so these glaciers provide this water at a critical time of year. And we say they provide a buffering capacity or protection from our summer drought. And I've always believed that the reason the Skagit River hosts all 5 native species of Pacific salmon is because of all the glaciers in that watershed that have provided stability even during the warmest summers during extended droughts. So water is important not just for ecosystems, but also for irrigation in Skagit County, for the hydroelectric industry, and a host of other reasons. And like Whatcom County, Skagit County has a moratorium on wells. And so our water resources, even in this really wet part of the world, are taxed pretty much to the limit already. And, whoa, I want to do that. Why won't it let me? So, the other reason we're really interested in these glaciers is that, as I said, they're changing really fast. And so what I'm going to show you in the next several slides are comparative images of glaciers from in and near these national parks in this part of the world and how they've changed. In some cases, it's going to be almost 100 years, and most of the slides are more like 40 or 50 years. And I want you, There are a couple things I want to draw your attention to on these. And first, with the yellow arrow, I'm showing you how far down the mountain the glacier came. In other words, where the terminus is. Because you'll see that the terminus has changed pretty dramatically. The other thing to keep your eye on in these images is how these glaciers have not just changed in area, but how they're thinning. So what I've highlighted here is what we call the trim line. And that's the line at which the ice used to be. And so you can see from that image just how much thinning has gone on, as well as a retreat. And so here's Helm Glacier in 2002, and you can see, I think, pretty clearly how much it's receded and also how much thinner it's got. So this is an example from North Cascades National Park. This is Banded Glacier. And in the 50s and early 60s, this glaciologist, Austin Post, did us a huge favor. He went all over the western US photographing the glaciers. So this is what Austin saw in 1960 on Banded Glacier, which is on Logan Peak. And then I had the glaciers rephotographed last summer, and so that's the change. And one of the things we're seeing, kind of a positive, I guess, if you like lakes, is that we're getting new lakes as we lose our glaciers. And so another example, South Cascade Glacier, and this is going back to 1929, and you can see the glacier filling this valley. And again, look at how high it is on the valley wall and how it comes around and there's no lake. By 1960, when Post was there, the glacier had receded from a position somewhere in here and has melted back around the corner and exposed South Cascade Lake. I had Scurlock rephotograph it in 2004, and you can see the glaciers melted even further back up the mountain. And hopefully you can get a sense that it's also getting thinner. And then what it looked like in 16. And so you can see a little bit in these images how sensitive these glaciers are. This wall of the valley faces southwest, and so you can see most of the thinning and melting is occurring on this side as compared to the shaded side. So these glaciers are extremely sensitive to the shadows that fall on them and from secondary accumulation sources like snow avalanches or wind drifting. And then moving across Puget Sound, yeah?
Comparison photos taken at the day of the year when the glacier is changing from net loss to net income.
Yeah, good question. We always want to get these photos at the end of the melt season because that's when most of the ice will be exposed and we can really see the margin, the terminus of the glacier. So these are all taken in late September or thereabouts. So this is Lillian Glacier, 1905. This is in the Olympic Mountains. And really stunning change there in about 105 years. Basically, that glacier is gone. There's a little patch of ice up in the top here, but not much. No crevasses, not much of any flow. And another example from the Olympics, this is Andersen Glacier, Curtis, 1936. And you'll notice how this whole valley is filled with ice. The glacier heads way up here in the Surt. Well, by 2004, the glacier is really diminished dramatically. Another lake is formed, but the ice used to, you can see a trim line right up here. So the glacier melted significantly back by 2004, and by 2015, there's some debris-covered ice under that rubble. There's still glacier, but it's largely gone. And then just one other example from the Olympics. This is Ferry Glacier. And this is just to the east of Mount Olympus, if you know the peninsula very well. And another example of a new lake and a glacier that's gone. So wherever we've been looking in the mountains and wherever we can go back very far in time, we're seeing these really dramatic changes in these glaciers. And so when we look at what's happened in the recent past at the national parks, the Olympics seem to be losing their ice faster. They've lost about 33% of their glacier area since '82. North Cascade's about 20, and Mount Rainier a little less, but remember Mount Rainier, that volcano is 14,400 feet in height. And so those glaciers extend to really high elevations. And the other thing about Mount Rainier is that there's a lot of debris cover. There's a lot of rotten rock on that mountain. And if you get more than a few inches of rubble or dirt on top of a glacier, it pretty much can completely stop the melting. So Mount Rainier is a headache for us and for monitoring the glaciers for a lot of reasons. But you know, as I said, it's not just the change in area. That's pretty easy to monitor from air photos or now from satellite images. But we really want to know that third dimension of loss, right? We want to know the change in thickness because that gives us volume change, which is directly related to the ecology of our lakes and streams and to the use of water. And to kind of illustrate this point, this is one of the glaciers I've been visiting since 1993. It's called Noisy Glacier. And last fall I was out there and on the glacier, and I noticed what looked like a small landslide from on the glacier, and I'm pointing at these rocks. And at the end of the day, we walked by there, and this is what we saw. And I was blown away because I had no idea the ice was that thin. And so here, where Graham is standing, there's just less than a meter of ice left. So this is one of our glaciers that's disappearing really fast. And so this need to know how their volume is changing led me to develop this glacier monitoring program in 1993. And so I'm responsible, as I said, for monitoring the glaciers in these parks, and every 10 years we get air photos to measure the area changes, but on the 8 glaciers shown by these colored dots, we do our intensive mass balance monitoring, and I'll explain what mass balance is in a second. I should mention that my program is patterned after South Cascade Glacier. You saw a few images of that earlier, and basically, you know, the methods for monitoring glaciers are pretty standardized globally. But I wanted to be able to match what they were doing at South Cascade Glacier, because one of the things we sought to learn is how representative that glacier was of the larger population. And as you'll see in a few slides, it's not very representative. So what we do is try to visit these 8 glaciers at least 3 times every year. And when we go, oh, here they are. There's a panel that shows the 8 that we monitor. So Blue and Eel in the Olympics, Emmons and Nisqually at Mount Rainier, and then Noisy, North Klawati, Silver, and Sandalee in the North Cascades. And we chose these glaciers for a number of reasons, not the least of which is that we could safely get around in them. And some of the glaciers, and this is another thing with Rainier, the ice falls so steeply off of that mountain that it's really broken by ice falls, which are really difficult areas to access, and it complicates our trying to measure melting on the surface, because now in a crevasse zone, you've got all this surface area. So we chose these glaciers. Also, we wanted them spread out across the parks. I put them in different watersheds because one of my goals for this project was to have it be long-term, and so I wanted them in different hydro projects. And that turned out to be a good idea because now I'm getting support from 3 different hydro projects in the park, Chelan, Puget Sound, and Seattle City Light. But when we go to these glaciers, we make 2 visits that are really critical. We go in spring, usually at the end of April, and we figure that snow accumulation, or snowfall season, if you will, is ending and melt season is going to start. And when we're there, we do a couple of different things. We measure the depth and the density of the snow that fell from the previous winter. And then we put these melt stakes in. And these melt stakes serve as our vertical reference. We can come back through the summer to our fall visit, which is usually the end of September, when we figure that melt season's ending and accumulation season is going to start. And we can measure how much of the snow and ice that was there, shown in white here, that remains. And so from these measurements, we get what we call mass balance. How much snow did it gain in the winter, and how much snow and ice and firn did it lose the following summer. And just a few images of some of the equipment we use to measure depth and density. This is actually a tank antenna from a Sherman tank in World War II. And that's the best thing that we have found for probing through this, what we call the Cascade concrete, right? This really heavy, wet snow we get. And I had a colleague, Andrew Fountain, from Portland State. He gave me his Rocky Mountain probe to use, which was a fiberglass continuous loop thing. And I brought it up to one of our glaciers, and I started jamming this thing. You know, and we're looking at accumulations of 6, 7, 8 meters on these glaciers. So it's a long way to probe. I'm ramming this probe down, and pretty soon everybody's laughing at me because the darn thing went down and it hit an ice layer, and it was coming up behind me. So I'm jamming this thing, and I'm going, yeah, this is a great year for the, and then everybody's laughing at me. So anyway, these tank antennas are the only thing that really work well in our Cascade concrete. We also use this not lightweight snow core and this not lightweight steam drill, which Mike is using here. So this is driving steam through this hose, and we can melt these holes, you know, a few centimeters in diameter, 30, 40 feet into the glacier in about 15 minutes to put our stakes in. So here's, and I don't have time to go over every one of the glaciers, so I'm going to focus on North Klawati as an example of what we do and what we've learned. And so we place these melt stakes down the center of the glacier from the top to the bottom. Okay, and so we make point measurements of accumulation and melt at these, and then we use them to calculate the glacier-wide or net mass balance. So I love this slide because it shows us at North Klawati Glacier at the end of the melt season. And one of the reasons I like it is that we were really lucky because I put that stake right there, and if I had put it over here, we would have lost that data point for the year. And remember, when I was there in the spring, I'm standing up here somewhere on 20 feet of snow or so, and so when I drill and I drop that stake in, there's a little bit of hope and faith goes into it. But it's hard to see, but I don't know if you can tell just how long this stake is. And here's an older stake from a previous year that we left in to capture some late season melt after our visit. But we're typically seeing 7 to 8 meters of melt on the lower parts of these glaciers. So more accumulation on top, more melt on the bottom. And this is the basic data. So each one of these plots or colored lines represents the data from one of those 5 stakes on North Kluwati Glacier. And as you'd expect, the upper stakes have a more positive balance. This is meters of water equivalent. And you can see they're kind of holding their own, but they're not really growing and adding much mass to this glacier. And this comes back to what I was saying earlier about there being less winter accumulation. But look at how much mass has been lost at these lower stakes. I mean, 80 meters of water equivalent, and this is just since '93, so about 25 years. And then, you know, the equilibrium line for this glacier, actually, I have it mislabeled, it should be right here at 0, is about 2,200 meters between these stakes. And so that glacier, the equilibrium line isn't anywhere near low enough to sustain the glacier at that size. So this glacier is in a period of really rapid adjustment, trying to reconfigure itself to the present climate, which isn't stationary either. But this is the basic data then, and again, it's balance in meters of water equivalent. And while these numbers seem sort of small on that scale, remember that that's averaged over a glacier that might be a square mile in area. So we're actually talking about huge quantities of water that these glaciers accumulate. And so the blue shows us what it gained in the winter. The red is what it lost the following summer, and then the purple is just the annual balance or the net balance. And so you can see just how variable our climate is on these glaciers. We have years where they'll get 3 times the snowfall they do in other years. And there's a slight tendency for years that we get really big snowfall for there to be less melting in the summer because we find that the weather conditions persist. This is one of the reasons it's a great place for glaciers is that the weather's really lousy here typically in May and June. It's perfect for glaciers because at the time of the solstice, there's thousands of feet of clouds typically over these glaciers. So the melting, that weather pattern when we get wet winters with heavy snowfall tends to persist into May and June and retard the melting a little bit. So this is our record for one glacier. And this plot now is showing you the net balance. I'm not showing you winter and summer, just the net for the glaciers in North Cascades. Similar scale, meters of water equivalent. And what you can see here, each bar is a glacier, and I don't know if you can see the whiskers from the airs associated with our measurements on there. That's a little difficult to see. I apologize for that. But when I started, the first 2 years were pretty negative. And again, that's the glaciers lost more in the summer than they had gained in the previous winter. Well, that started to turn around in the late 90s, and for 5 of the next 7 years, the glaciers gained more in the winter than they lost in the summer, which was kind of surprising to me, because I thought going into it that, you know, we're just on a really declining trend with these glaciers. But what we're seeing here, this mass that was accumulated in the late 90s was lost in the early part of the 2000s. And so we went through a really negative period only to jump back to positive, right, for a few years around 2010, 11, 12 in that area. Since then, now we've gone back the other way. And so what we're looking at here is our Pacific decadal oscillation, right? The climate here varies from cool and wet to warm and dry in about a 20-year cycle. And so that's what we're seeing in this data. And you know, there are a lot of ways they measure the Pacific decadal oscillation, but I don't think anything that I've seen is as sensitive as the glaciers are. And it shouldn't be surprising because they're so sensitive to the weather. To look at the trend for the glaciers, we can do what we do the cumulative balance. So we just take the net balance and either add or subtract it every year, right? And we get this time series. And so these are the glaciers in the North Cascades since we started in '93. Here are the ones in the park, and here's South Cascade Glacier, and I think you can see that South Cascade, I don't know why I did that, South Cascade isn't very representative of, sorry about that, of the glaciers, other glaciers in North Cascades Park. And so we're looking at, you know, over here at some of our glaciers, a loss of 12 meters of water equivalent, or pushing 40 feet on a glacier that's huge in area. And then just the data from the glaciers at Mount Rainier in the Olympics, and all I want you to see really is that it's the same negative trend, right? These glaciers are losing a lot more mass to melting in the summer than they're gaining in the winter. So I want to conclude with just a few slides on some of the implications of the losses of glaciers, with just one example from the Skagit Valley. And I want to bring it back to the issue of water. And I want to focus on the Skagit River watershed because it drains about 75% of North Cascades National Park. It's the largest stream draining into Puget Sound, and it has the largest number of glaciers. And so a former Western student who works for me, Mike Larrabee, and I published a paper last spring on the contribution of glaciers to water flow in the summer on the Skagit River. And we used a couple of pieces of information. This is our cumulative balance again, but this time I've extended it back from 93 to 59 by using old maps. Okay, so we made these geodetic measurements of volume loss up to 93, and then we're using our surface measurements. And so we start with a zero balance. We see the Pacific Decadal Oscillation really clearly, and over that period of time, about the average loss is about minus 20 meters of water equivalent for the glaciers in the North Cascades. So if you multiply that 20 meters by the area of all the glaciers, you get at the volume loss that's occurred. The other information that we used looks at how the glaciers have changed with elevation. So this plot here is showing the area of glaciers and these 50-meter elevation bands. And the black bars show where the glaciers were in 1959, how extensive they were in the bands. And then 2009 is shown by the white. And I was able to do a check on this air photo interpretation with the Shuttle Radar Topography mission. And so, as you'd expect, most of the loss is occurring at lower elevation, where there's less accumulation and where it's warmer. And it turns out that the average equilibrium line for glaciers in the North Cascades is right around 2,200 meters or so. So not much change in higher elevation glaciers, but huge changes in the lower elevation. And this is important because a few years ago I was asked to testify at the state Senate hearing on climate change, and I was asked the question by your state senator Doug Erickson if there were any glaciers that weren't changing that fast. And I know where he was going with this, but the reason I bring it up is it's important to understand that the fastest change is occurring down low. But you could go up high, probably in any mountain range, and find a small glacier that's maybe in the shadows, that's getting secondary accumulation from avalanches or wind drifting, that isn't changing nearly as fast as the others. Okay, so I've seen other people, including the guy that testified after me, kind of try to misuse that information. And say, well, some glaciers are growing and some are shrinking. But there's a lot more to it than that, as you expect. So the other information that we use to get at this are these melt curves. And so we're looking at snow, firn, and ice melt in meters of water equivalent, again, by elevation. And we're looking at two different summers. 2010, a cool summer shown by the dashed lines and the open boxes. And then a really warm summer where the melting was about 1 meter to 1.5 meters more. And so what we did is just multiply the melt in a given elevation band by the area in that elevation band, and then we summed it all up. And that's how we got at how much water these glaciers are contributing. And so what we learned was pretty staggering for the Skagit watershed. The first thing what we learned is that the amount of water the glaciers are delivering to the river every summer has declined about 24%. So here in Skagit County, much of the water in the Skagit River is used for irrigation, hydroelectric, and I mentioned this moratorium, but our water resources aren't fixed. They're declining, you know, and it's the summer when we're really stressed for water. So that was staggering to learn that that much has been lost, and it turns out that loss is equivalent to about 800 billion gallons of water. And as we use water in Skagit County, that's about 100 years of water supply. And again, that's how much more melting there has been than accumulation, and a measure of how much these glaciers have been diminished. But with that, we understand that the Skagit still provide, or the glaciers I should say, still provide about 6 to 12% of the summer runoff for our glaciers. So they're still important, even though they've been greatly diminished. So with that, I am going to stop and ask for questions. And please let me thank you for inviting me here today.